Thank you very much. So today I'll give the third lecture on A-model topological string theory. So recall that last time we talked about the topological vertex. So let me give you a brief review of what we did last time. I also would make some additional comments. So recall that we have the Agnaghi, Clem, Marino, and Vafa's physics theory of topological vertex. I summarize it as O1, O2, and O3, O for open. And then I describe the mathematical theory of topological vertex developed by Jun Li, Kefeng Liu, Jianzhou, and myself, LLLZ. And I describe it in details. And the steps can be summarized as R1, R2, and R3, where R means relative. So let me recall the construction. The topological vertex is a generating function. In the physics theory on the left-hand side, it is a generating function of open Gromov-Witten invariance of C3 relative to 3 Lagrangians. And then each Lagrangian Li is also equipped with a framing. So we call them Li-Ni frame Agnaghi Vafa Lagrangian branes. These Ni's are integers. And the C mu or mu is a triple of partitions. Mu upper I correspond to the winding numbers associated to the ice Lagrangian. And this generating function is denoted when we fix the framing and fix this triple of partitions, and we sum over all the possible topological type of the domain. So the existence of this generating function of invariance is predicted by Agnaghi, Clem, Marino, and Vafa. So to define this, so we can actually form the moduli space of such maps, and we can use the compact Calabi-Yau torus to define the invariance by localization. But if we do that, we won't be able to get a general framing depending on 3 independent integers. But we can do it by considering relative Gromov-Witten invariance. The building block is of our formal relative Gromov-Witten invariance is the formal relative Gromov-Witten invariance of an indecomposable relative formal toric Calabi-Yau threefold associated to this kind of graph. So you see this graph, because our vertex, so we have so W1, W2, and W3 are weights. So they are so this Wi, recall that they are character of the Calabi-Yau torus. So let's say it's generated by a basis. And there's the Calabi-Yau condition is W1, W2 plus W3 is 0. And here Fi is And Fi, so this framing vector is Wi minus Wi plus 1 minus Ni Wi, where Ni is some integer. So the most general, this kind of decomposable relative formal toric labial. So what are the dependents? So it depends on W1, W2, and N1, N2, N3. Since W3 is negative W1, negative of W1 plus W2, and Fi's are determined by Wi's and the integer Ni. And then, so the geometry, this is the graph, and the geometric picture is on the right-hand side. We have a configuration of 3 P1s, C1, C2, and C3. They come with like its formal neighborhood. And so the corresponding, so the Ni correspond to the splitting of the normal bundle of Ci in the formal toric threefold. We actually define, so there's a moduli of relative stable maps to this configuration, counting curves such that it maps to this configuration of 3 curves. And we also specify the ramification pattern along the divisor D1, D2, and D3. And the ramification patterns are specified by the 3 partitions mu1, mu2, and mu3. We define and compute by localization, but a priori, this invariance should depend on mu. So the 3 partitions, mu1, mu2, mu3, the 3 integers, n1, n2, n3, and a priori, it also depends on W1, W2. But actually, we can prove, and it's a highly technical proof, that this actually is independent of W1 and W2. So that's the first part. So I also want to emphasize the following. The formal toric labial threefolds are generalizations of this kind of the formal neighborhood of, so suppose that you have a honest toric labial threefold, and this is one skeleton. You take the formal neighborhood is a formal toric labial threefold, but it is more general than that. So let me first make the first point. So for example, you see that we can allow this kind of graph. So we only require locally planar. So you can actually consider a graph which is actually on a torus. Yeah, let me draw in this way. So consider an abstract graph. It's locally planar. And then you have W1, W2, W3 on one side. And this edge is identified with this edge. And this edge is identified with this edge. So here W3 is minus W minus W2. Okay, so if you consider so what happens is the following. So somehow you glue these two C together to get the P1. So you will actually get this kind of this configuration. So this is C0, C1. Oh yeah, maybe let me write. So this is C1, C2, C3. So actually we have a configuration of 3 P1s, like intersecting at the north and south poles. And the normal bundle of each CI on the whole thing is O minus 1 plus O minus 1. And we can define this. So this is does not come from an honest Tory club Yale. But these are we can define them as formal relative Gromov-Witten invariants. So we see that this is actually more general. And the second point I want to make is this is also more refined. For example, we can take, say this is the gamma is the gamma of X, where X is the total space of O P2 minus 3. So we know the second homology class is generated by the class of a line in the zero section P2. However, if we take this graph, I mean, even if we don't count, so first, if we take this graph, so in our construction, we will take this graph and add framing, compactify this 3 copies of complex line and to get complex projective line. So this correspond to, so this D1, D2, and D3 correspond to putting L1, L2, and L3. So, but here, the open invariance will depend on genus. So we have open Gromov-Witten invariance. So this will depend on genus relative degree. And we also have close Gromov-Witten invariance. So just usual close Gromov-Witten invariant counting close holomorphic curves. So then they will not touch these Lagrangians, and their image will be in the base P1. And we know it's depend on D. Yeah, so it's just a non-negative, let's say consider non-constant map, then it is some positive multiple of, so we can consider degree for each non-negative integer G, and for each positive integer D, we have this Gromov-Witten invariant of this total space OP2 minus 3. We have Gromov with genus G degree D Gromov-Witten invariance. So in the relative setting, to get a close Gromov-Witten invariance, it corresponds to we take like we just put empty partition. So meaning that our curve does not intersect these three divisors. Then the curve will cover in our like this relative formal toric labial threefold does not have this. It like if we focus on this base P1 and here sorry, the base P2, this formal toric labial only has like a formal neighborhood, so it does not have like this P2. And as a consequence, we can so the second so the second homology, the class of this Y hat is actually a 6-dimensional. And if you let, so you specify the empty partitions, these will correspond to close Gromov-Witten invariance, but you can still have NG D1, D2, D3. And then we see that, so this is the OP2 minus 3, GD is equal to yeah, so it is also more refined in the sense. Okay, so if we have an honest toric labial threefold, so we can form this generating function of closed Gromov-Witten invariance. So this Z is the disconnected version. It's generating function of a closed Gromov-Witten invariance with possibly disconnected domain. And you see that, so let's compare the gluing formula in the physics theory in terms of opening invariant and our degeneration formula. Let's take the simple example, which is the resolved conical O minus 1 plus O minus 1 over P1. So in this case, we first put so the one-dimensional orbit closure consists of 5 orbit closures. The zero section is a projective line, and there are 4 complex lines, just C. And in our setting, we first compactify the 4 complex lines to complex projective lines. And by adding divisors at 4 divisors and infinity, and this corresponds to, in the open picture, putting 1 Lagrangian on each of the complex lines, torus invariant complex lines. And in the physics set, in the original topological vertex, so they put a Lagrangian, which will intersect this zero section P1 along a circle. And then to get the closed Gromov-Witten invariance, we just say, okay, so we just count closed curve, which means the closed curve will not intersect this 4 Lagrangians. And so it will only cover the zero section. And then this Lagrangian cut this one skeleton into 2 pieces. And the left-hand side, yeah, we put a generating function. So this is, so left-hand side will just be a border counts covers of border Riemann surface of this embedded disk in the left-hand side with some winding number. So you see that the gluing formula looks like this. And we have similar gluing formula, actually exactly the same gluing formula, and we just replace the open Gromov-Witten invariance C by our relative Gromov-Witten invariance C tilde. So we have exactly the same gluing our degeneration formula match exactly with the gluing formula. Oh, so here's some notation. So here for a partition mu, which consists of so let this absolute value notation is like, this is the size of the partition, is the sum of the components. The length of the partition L mu is the number of components, and kappa mu is just some number given by this formula. And recall that, so the third part is, so if we want to show that our algorithm is exactly the same as theirs, we should show that our C tilde is equal to their C. So they provide a closed formula for, first of all, the dependence on framing is given by this. Recall that, so the left-hand side depends on lambda. So here, it turns out it can be written as a function of Q, where Q and lambda are related in this way, and W is somehow complicated, but it's complete explicit. We actually also have a closed formula. Looks very similar. And of course, it happens to be the same. So when we finish our paper, we cannot prove like RW and RW tilde and their W are the same. We can prove that based on using the previous work by with Kefeng Liu and Jianzhou and myself, we can prove that they are the same. So we can prove. So it follows from, maybe I'll say that using, we prove so when one of a partition is empty, and then we have this explicit expression W tilde, and then we send it to Lam, and he composed some computer program, and they are equal. Like if you plug in any triple of partitions, they are equal, but it seems to be difficult to prove this like by purely combinatorics. It's an identity in classical symmetric functions, but it seems to be very difficult to prove it by purely combinatorics. Yeah, we asked experts. So as I said before, so a technical lemma is that, yeah, this invariant is independent of W1 and W2. So here is a corollary of this. So for any Horry-Calabi-Yau threefold, we can, the moduli space M bar G 0 x beta may not be compact. But we just use this localization formula to define it. Because it turns out that if you have a stable map to X from a closed Riemann surface, and more generally a pre-stable algebraic curve of genus G, the image must the image will be contained in the configuration, the one skeleton, and actually it is contained in the union of torus invariant P1s. So the torus fixed point is actually always compact. So we can use this formula to define equivariant invariant. But then now this equivariant invariant is in general a rational function in U1 and U2. Recall that U1 and U2 are the generators of the cohomology T prime equivariant cohomology ring of a point. And this is actually homogeneous of degree 0. So it's actually a rational function of one variable, U1 over U2. So if we just like theoretically, it should depend on this It's a rational function of this one variable. But a consequence of our technical level and our algorithm implies that this is actually just a rational number independent of this U1 over U2. So the fixed point set of the like three-dimensional torus and the two-dimensional torus T prime are the same. But in general, if you replace this independent of weights, independence of equivariant parameters, this independence is not true if we use the larger torus, the three-dimensional torus. So if you use the three-dimensional torus, you use the T equivariant, not T prime equivariant Euler class of the virtual normal bundle of the torus fixed point set in the whole M bar G0 X beta. So then it will be a rational function of the three equivariant parameter U1 and U2 and U3 homogeneous of degree 0. And if you use this in general, it will depend on these parameters. So that's what I want to comment on this. And finally, so for the third part is the closed formula. Now I want to say a few more words about, so I want to say a few words about the relationship between the topological vertex and the Gromov-Witten-Donaldson-Thomas correspondence. So if we look at the this combinatoric this expression W, so it curly W, mu1, mu2, mu3, so it depends on three partition. Oh, can I ask a key fact to have such an independency of U1 over U2? Since it was defined through a localization first. Yeah, it's not obvious, and we we prove it. It's a long technical lemma from our point of view, but actually it also follows from the Gromov-Witten DT correspondence. Because once we know that Gromov-Witten DT correspondence is true, so which I'll say a little bit more later. If you look at the computation on the Donaldson-Thomas side, it is obvious that it will be independence of U1 and U2 if we if we use the two-dimensional Calabi-Yau torus. So now it's better to see that in that way. So a conversion. So Eknagich, Claire Marino, and Vafa got this expression by consider the color home flip polynomial associated to this actually this link with three components. So each component is colored by a representation of the unitary group. And so they correspond to partitions. So Konkovic, Tiking, and Vafa, so they're in their joint paper, they realize, so this combinatoric expression is actually a generating function of 3D partitions. And a generating function of 3D partition is actually a generating function of Donaldson-Thomas invariance of C3. Donaldson-Thomas invariants are virtual counts of ideal sheaves. So if you do localization, then the ideal sheaves in C3, which are fixed by the torus action, are monomial ideals. So the monomial ideals correspond to 3D partitions. And so I think this actually motivated the famous conjecture by Molikny-Cross of Okunkov and Pender-Pender. So once you recognize this, and it is natural, so you see that the left-hand side is supposed to be Gromov-Witten invariance. Now you see the right-hand side is some Donaldson-Thomas invariant. So this allows them to, they make this conjecture which goes beyond the toric-Labial case. So they conjecture a correspondence between Gromov-Witten invariance and Donaldson-Thomas invariance for smooth projective threefolds. So they wrote the first paper, they had this conjecture for Calabi-Yau threefold. And the second paper, they generalized this to general projective threefolds, which are not necessarily Calabi-Yau. And then, but the toric Calabi-Yau threefold is never projective, it's never compact. So they also have a equivariant version. They have equivariant Gromov-Witten Donaldson-Thomas correspondence for the equivariant Gromov-Witten Donaldson-Thomas invariance for certain smooth quasi-projective threefolds. In particular, I mean, for toric threefolds, we can define equivariant Gromov-Witten invariance and the equivariant Donaldson-Thomas invariance, and they can be computed by localization for any toric threefolds. And also another example is if you take the total space of two line bundles over C. So this is a non-compact threefold, and you can consider equivariant version. You let C star to acting on the fiber and fix the base, and this allows one to define a equivariant version, and one can also formulate an equivariant Gromov-Witten DT correspondence for the so-called local curve in a threefold. And in their first paper, they also show that the Gromov-Witten DT correspondence for smooth toric Calabi-Yau threefold is equivalent to the Agnagic-Marino-Vafa algorithm of the topological vertex. And by localization, the Gromov-Witten invariance of smooth toric Calabi-Yau threefolds can be expressed in terms of the Gromov-Witten vertex. So the Gromov-Witten vertex, you can think them as it's generating function of open Gromov-Witten invariance of C3. And then the localization actually reduce it to a generating function of Hodge integrals on M bar Gn, the moduli of curves. On the other hand, the DT invariance of smooth toric labial threefolds by localization can be expressed in terms of the DT vertex. The DT vertex is a generating function of DT invariance of certain generating function of DT invariance of C3. And by localization, it's a generating function of 3D partitions. The Gromov-Witten DT, oh, sorry, I should say that the Gromov-Witten DT so by localization, Gromov-Witten DT correspondence of toric labial threefolds can be reduced to the equality of Gromov-Witten vertex and DT vertex. So maybe let me give you an idea like how this three partition Hodge integrals. So these are the, so if we look at so we can consider moduli space of maps from border Riemann surface. So yes. Okay, so this is has G handles and holes. So this gives us some moduli space. And then if we compute, we can compute, so this moduli space, so this gives us a moduli space, say M, G, so this three Lagrangian is not invariant under the big torus, three-dimensional big torus, and it's not invariant under the Calabi-Yau torus, but it's invariant under the I shouldn't say invariant. I want to say that each of this Li, so this T prime R, which is the maxima compact subgroup of the Calabi-Yau torus. So this is compact Calabi-Yau torus. So it acts on C3 and also it preserves each Li, not pointwisely, but it acts on, it restricts to an action of each Li. So as a consequence, it has an action. So this compact labial torus acts on the moduli space of such stable maps to C3, like from border Riemann surfaces such that the boundaries are mapped to this three. And of course, we actually should allow the domain to have nodal singularities. And actually, if you look at the like T prime R fixed maps in the setup, so actually the whole homogeneous curve is mapped to the origin. And then you have certain, and it's a union of this closed curve and with disks, like one disk for each boundary component. And so then, so this degrees gives us the first partition mu1 and so on. So this is the fixed curve. So you see that the moduli, so this moduli space can be identified with up to some finite, so up to some finite cover. This is just M bar G, let's say. So when we do localization, when we compute this open Gromov Witten or define and compute this open Gromov Witten invariance by localization, we actually just get some integral on this moduli space of stable curves. Yeah, actually, it looks like this. So this automorphism of, and there are some, open invariants, there are some choice of sign. So here the W1, W2, and W3 are the tangent weights at the origin of C3. So here it's Okay, so yeah, it looks complicated. So let's see. So the first line is kind of clear because it's just depend on W, and here mu is a triple of partitions. And then for each triple of partition, we have so the component of mu upper I is called mu upper I lower j. So up to the length of this partition. Yeah, so the first line is just this. And the second line, so this psi is just, oh, so L1 is equal to 0. L2 is the length of mu1. L3 is the length of and the psi, recall that the psi is the C1 of the cotangent line. So this Li is Li at some curve. So let L be L. It's just the cotangent line at the I smart points. And here, this is finally this notation. So let's introduce some polynomial in U. It's a degree G polynomial. So the coefficients lambda I are the ith chain class of the Hodge bundle E. So recall E is the Hodge bundle. So if this is a smooth genus G curve, then this is just the space of holomorphic differentials. Yeah, so maybe let me right, so this is so we call them like three partition Hodge integrals. Yeah, so basically this Gromov-Witten vertex after localization is just a generating function of three partition Hodge integrals. So the equality of the Gromov-Witten vertex and DT vertex is some formula for such Hodge integrals. Okay, so now let me. Oh, so let me just say that so Molly Oblonkov and Okunkov and Pender in 2008, they proved the Gromov-Witten correspondence for equivariant primary invariance for any smooth toric threefolds. So it's not necessarily Calabi-Yau, and it can be compact or non-compact. In particular, this will imply the Gromov-Witten DD correspondence for toric clubial threefolds and restricted to the clubial torus. This shows that the algorithm of topological vertex proposed by Agnelli, Clem, and Marino and Vafa holds for in general. And this will imply this W is equal to W tilde. Yeah, so which is holds in general. So welcome back, thank you. So yeah, I see a question in the chat. Can formal toric varieties be described by fans? No, they are not in general described by fans. They are described by graphs. The GKM graphs. So that's the answer of the question. And now, so the last thing we talk about before the break is that there's a Malik, Oblomkov, Okunkov, and Panda in 2008 proved the Gromov-Witten-Donaldson correspondence in the equivariance setting for primary invariance for any smooth toric threefolds, not necessarily clubial, since it's like general toric threefolds, so we cannot define the so-called clubial torus. So this is like fully equivariant in 3 equivariant parameters. And in particular, if we specialize this to clubial threefold, toric clubial threefold, and clubial torus. So this is this implies the topological vertex, the algorithm of topological vertex. And then I want to mention that there's another theory which is closely related to the Donaldson-Thomas theory by wall crossing. The Donaldson-Thomas theory is like so both are like sheaf counting theories, and they are integers. So in the absolute version, so DT invariants are virtual counts of ideal sheaves of curves. And PT invariants are virtual counts of stable, so-called stable pairs. And they are actually related by wall crossing. So by now their relationship is known. So I would like to, give you some, so you see they proved this, and then 2 years later, so Panda and Pixon proved that the Gromov PT descendant correspondent for smooth toric clubial this is smooth toric threefold. So this generalized the result of MOOP from the primary invariance to descendant invariance, right? We define the descendant invariance. For general projective manifolds. And also in the same year, they actually also proved this beyond the toric case. Gromov-Witten PT correspondence for a fan or a clubial smooth threefold, which is a complete intersection of product projective spaces. So they prove it for descendant invariance, so such that the insertions are even cohomology classes. Yeah, so for a long time, this is the record. So let's go back to a few years. So what are the other cases of Gromov-Witten DT or Gromov-Witten PT invariance that have been proved? So even before they proved this toric case, so they have the Gromov-Witten series. They have proved the correspondence for Gromov-Witten and DT theory for local curves, namely the total space of a direct sum of two line bundles over a smooth curve. So on the Gromov-Witten side, the theory is completely solved by Brian Panda, and in the DT side, on the DT side, the theory is completely solved by Okunkov and Panda. And then this proves the Gromov-Witten DT correspondence for local curves. Okay, so for a long time, so then finally there's like big result by John Pardon. Well, you see this is like much more recent, actually just last year. So he proved the Gromov-Witten DT or PT correspondence for any smooth projective threefold X such that the C1 is non-negative. Yeah, so I think this is the best results of the Gromov-Witten DT correspondence. Okay, so that's so the next thing is there's some generalization to orbifolds. Actually, Gromov-Witten invariance can be defined for orbifolds. So this was defined in the early 2000s. The algebraic version is due to Ambromovich, Graeber, and Vistoli. It's like previously, I mean, they can only, oh, sorry. So when the target is, they prove it for toric threefolds and they prove it for local curves. So and then they prove it when your smooth, you have a funnel of Calabi-Yau threefolds, which is a complete intersection of product of projective spaces. So in any case, there are the three classes of examples, but there are special cases. And Pardon actually can prove, so before there are like conjectures, so before there are conjectures by MNOP, right? And the conjecture of MNOP are proved in like the three classes, like toric threefolds, local curves, and complete intersection in a product of projective spaces. So then Pardon can prove this for any smooth projective threefolds such that the C1 is greater or equal to 0. In particular, any projective Calabi-Yau threefolds. So it's a general, much more general. Yeah, so he proved it more general, and then you see this generalization takes many years. Okay, I guess that answers the question. So next I want to mention, so you see that this Gromov-Witten DT correspondence, thanks to Pardon, is now has been proved in like great generality. So how about the orbifold case? So you see that this Gromov-Witten, there are something which is very special for like complex 3-dimension. I guess from the physics point of view, the complex 3-dimension is also very special. Gromov-Witten invariants are defined in any dimension, right? We, like our first lecture, it's for any dimension, Kähler manifold of any complex dimension. But the DT-PT invariants are defined just for threefold. Of course, more recently now they have been defined for fourfolds too. Yeah, but so this is really this correspondence is really about threefolds. So now, on the other hand, so Gromov-Witten invariants have been defined for orbifals, yeah, more than 20 years ago. And how about, so Brian, Cadman, and Young, they defined DT invariants for Clavial 3 orbifol, so orbifol DT invariants. And DT invariants of toric, so the title of their paper is actually orbifol topological vertex, but it's actually the DT vertex, orbifol DT vertex. So you see, by the same reasoning, if you have a toric Clavial 3 orbifols, then you can compute the DT invariant by localization. And it should be expressed in terms of the orbifol DT vertex, which should be which is actually a generating function of color 3D partitions. So more precisely, a toric Clavial 3-fold can be obtained by gluing C3 charts. So the building block of DT invariance toric Clavial 3-fold is the DT invariance of C3. But for toric Clavial 3 orbifols, the charts are affine toric Clavial 3 orbifold. So it's C3 quotient by a finite group, and this finite group is containing, it's abelian. So we may assume it's containing the torus, and also because the Clavial condition is actually in the special linear group. So yeah, actually this is the, so this is the, yeah, so these are the charts. So then if we do localization, so we get monomial ideals, but they also, these monomials are also like, so the G, so each monomial, so the G acts on these monomials with some weights. So this 3D partitions, which correspond to monomial ideals, so they are colored by G characters. So the orbifold DT vertex is a generating function of color 3D partitions. So Dusty Rose, show that Gromov-Witten invariance of toric Clavial 3-fold can be expressed in terms of the orbifold Gromov-Witten vertex, which is a generating function of abelian Hurwitz-Hodge integrals. So instead of like integrals over m bar gn, you will get integrals over m bar gn whose target is not a point by the classifying space of finite group. So now what is, can we generalize the Gromov-Witten DT correspondence to toric Clavial 3 orbifols, or more generally, just three orbifols? Oh, let's see. Sorry. Yeah, so the Gromov-Witten DT correspondence for toric Clavial 3 orbifols is in general not known. Even the conjectural even the statement is not known. But they have been proved when the toric Clavial 3 orbifol has only transverse AN singularities. That means they are not glued, they are just be glued by some like special, not the most general C3 mod G, but it's given by like C2 mod by mu m plus 1. So if you take the stacky quotient, it's a smooth, so the weights is like on x and y coordinate are opposite. So it's a toric labial surface and times C. So if you consider just the usual quotient, C2 mod mu m plus 1, you get AN singularity. So this is, so we know that to prove this correspondence in general, it reduced to prove the Gromov-Witten equal to, yeah, so to prove the Gromov-Witten DT correspondence for orbifold vertex of this particular type. And in the 1-leg and 2-leg case, this was proved by Dusty Rose and Zheng Yuzong. And the full 3-leg case is, yeah, proved by Dusty Rose. So this is the, yeah, this is status for general, more general toric labial 3 orbitals. I think right now it's not even know what the statement looks like. It should be much more complicated than the smooth case. Okay, so that's what I want to say about the topological vertex. The third part is the, yeah, no, it's not remodeling conjecture. So this is another algorithm, and this algorithm will work for general toric labial 3 orbitals. So it will, yeah. So it is particularly useful, yeah, when the vertex, topological vertex, when the orbifold topological vertex algorithm is not available. But let me start with some overview. So this is actually a version of mirror symmetry. So mirror symmetry, we have A model and B model. So now A model X is a toric, yeah, it's actually a symplectic toric labial 3 manifolds or 3 orbifolds. And omega is a symplectic form. So as a complex orbifold, so this includes the manifold case, but so here it is the comes from the symplectic quotient. And it's also, yeah, so we take the stacky quotient, and it's also the if we forget about symplectic structure, it's as a complex manifold or orbifold is the GIT quotient. Yeah, of the complex torus. So there's a like coarse moduli space, which is just a GIT quotient. So this is a simplicial toric So this is simplicial toric labial threefold, which is a semi-projective. So as a simple example, so in the smooth case, so this is the A model geometry. So for example, the resolved conical is fine, but then O minus 3 plus O1, so this is not semi-projective. So this is, we need some honest symplectic toric labial threefold, not the formal one. Okay, so this is A model geometry. So the mirror symmetry. So the mirror should relate A model on this symplectic labial threefold to the complex geometry B model of the mirror. So this mirror, like X check Q, is the Hori-Vafa mirror. Oh. What happened? Let's see. Sorry, it's frozen. Let me just, yeah, try to. This is called so-called the Hori-Vafa mirror. And omega is a holomorphic three form. More explicitly, XQ is of the following form. So this is a hypersurface in C2 cross C star 2. So the coordinate on C2 are UV, coordinates on C star 2 is XY. So it's UV by X. So this is this is explicit, can be written down explicit if we are given the toric data of our originals, toric labial threefold. In particular, yeah, so this can all be described in terms of fence. And then this HXYQ, so HXYQ. Oh, so here K is the, so I should say that here K is the number of scalar parameters. And now Q is complex parameters. So this is an equation. So maybe let me say more later. Yeah, so the number of, the number of complex parameters is equal to the number of scalar parameters. And omega q is given by this. You take the residue along this hypersurface. Of this standard holomorphic form on C2 times C star 2. Yeah, so that's the holomorphic 3 form. So this is the B model geometry. So now, yeah, maybe let's see. So on the A model, under the mirror symmetry, the A model topological strings this symplectic toric labial 3 manifold or orbifold. So we know that they are Gromov-Witten invariants. So now we will consider generating function when we fix G and sum over possible degree. We also have generating function of open Gromov-Witten invariance, which is F, G, and X, L. And now we consider single agnagic Lagrangian brane, and we need to specify a framing F so that this invariants are well defined. So under mirror symmetry, so this should correspond to B model topological strings on this mirror. Okay, so for example, let's say we fix some Q. So the genus zero invariants are just classical period integrals of this holomorphic 3 form. But for this O genus Gromov-Witten invariance, there is a higher genus invariant by Brzezinski, Tchaikovsky, Ogri, and Vafa. So they have this invariant depend on T and T bar. And there's some holomorphic limit, which is conjecturally related to the Gromov-Witten invariance. So this is physics, and there's a mass. So years ago, Costello and Lee, so they want to define mathematical theory, and they have defined some like ancestral descendant, which is, but this is not defined in general, and it's difficult. So now, but what does so let me. So what is the Bouchard Lam Marino so BKM B or BKM P remodeling conjecture. So they have it 2007 for smooth 2008. So first they conjecture it for smooth toric labial 3 flow and generalized to smooth toric labial 3 orbifolds. It's now called the remodeling conjecture, because the title of their paper is the first paper is remodeling the B model. So that's called the remodeling conjecture. So the remodeling of the B model says the following. So they say that this BCOV theory, which gives us this mirror. So there's some dimensional reduction. Can be reduced to the theory of the mirror curve. So I'll say the frame. And this phi is some basically like log YD. I'll be more precise later. So basically, so the thing is, in the Torrey-Claviel threefold case, the remodeling B model said actually you can compute the B model topological string just using like this. You see this right-hand side define a hypersurface in C star 2. It's just a fine curve in C star 2 depending on Q. And this there's the so-called the Chekhov A naught Orrington topological recursion. So I will I will describe the definition precisely, but this is outline. So this can be mathematical defined. And actually it's really just one-dimensional complex variable. It's just in terms of this affine curve in C star 2. So this is defined, so this is mathematically defined, and we have a sequence. And here, so the topological, so the conjecture is that basically the open invariance can be extracted from this Aina-Orrington topological recursion. And also the close invariant is like omega G0. So this is n greater than 0. So this is the conjecture. So now it's good. So so now the A model, I will give the precise definition, but we have moduli space and we can define this generating function of the open and close invariance. They can be defined using localization. So yes. Yes. And then now I will also review the definition of this invariance defined by topological recursion. Well, so now both sides are like mathematical defined, and they conjecture a precise relationship between this B model invariance and A model invariance in all genera, and including the closed sector and open string sector. So this can be viewed as a version of O genus open-close mirror symmetry. So A naught so they prove it for a smooth toric labial threefolds. And then so in joint work with Bo Hanfang and Zheng Yuzong, so Zheng Yu is at Tsinghua University. So we do it for like this semi-projective toric labial three orbifolds. Oh, this also assume like it should also be semi-projective in the smooth case. And also there's some work in progress. So our orbifold version, as I will mention later, is actually more general than the version they originally conjecture. So in the original conjecture, we can have orbifolds, but the Lagrangian are still smooth. So we also proved the version where the Lagrangian can also touch the orbifold point, so the Lagrangian can also contain orbifold points. And actually, in working progress, so this Yu Song is a postdoc at like Yale's Mathematical Science Center. And Zheng Yuzong. So we have a statement for descendant, like equivariant descendant. So yeah, I think maybe, okay, so maybe let me, so then this is an overview. So in the last lecture, so we will first define the like A model geometry topology and also define A model topological strings. Like in like the open sector and closed sector, and also the descent and primary and this descendant. Because in our setup, we have defined this descendant Gromov-Witten invariant for general projective manifolds, but now we will define them for orbifolds, but just restricted to like toric labial orbifold, 3 orbifolds most. And then we will describe B model geometry, the geometry and topology of the mirror curve, and the B model topological string. And then we will describe, so we will outline the proof. So the and also, as Daniel requested, I think I will also say more about the TT invariance and relation between DT and PT next time.